In physics, there are four fundamental forces that govern the entire cosmos. The strong force, carried by particles known as gluons, binds quarks together to make protons and neutrons. The weak force, carried by W and Z bosons, rules radioactive decay, the process in which atoms can turn into others and irradiate nuclear energy. Gravity, still somewhat of a mystery to quantum mechanics, works with mass and dominates interplanetary scales. The last, and perhaps the most vital for the study of astronomy and even life on Earth, is electromagnetism. Carried by the photons, it's responsible for radio, X-rays, the heat of our sun, and most important, all the light in the universe. We mentioned electromagnetism before in a previous episode while talking about magnetic fields. Now it's time to explore it more thoroughly, talk about the many forms this energy can be perceived and its uses. In other words, let's talk about the electromagnetic spectrum. Light is a wave of alternating electric and magnetic fields, most of it completely invisible to us. The more energy the wave has, the higher its frequency, which is the same as saying it has a shorter wavelength. The electromagnetic spectrum is the whole range of energy states light can have, from as faint as the cosmic microwave background to as powerful as the strongest supernova. Photons can transmit information, heat, colours, and much more. Think about waves in the ocean or sound propagating through air. The faster these waves are, the higher their frequency. Conversely, as they get more frequent, they have to shorten their length to occupy the same space. If you want to say more words in the same amount of time, you've got to talk faster and spend more energy to do it. Light behaves pretty much the same way. The more energy a photon has, the higher its frequency and shorter its wavelength. This is important because different materials can absorb or reflect different wavelengths of light. A green leaf, for example, absorbs all the visible light from the sun except the green frequency, which it reflects back, making it the only one to enter our eyes. But the light we can see makes just a tiny portion of the larger EM spectrum, with wavelengths ranging from as large as the entire Earth to as small as an atomic nuclei. Because of this large range, the properties of light can vary drastically, based on wavelength. Let's explain a little about each of them. The less energetic type of electromagnetic radiation are radio waves. Their wavelengths are large, making them perfect for long-distance propagation. Radio waves have the ability to pass through the atmosphere, foliage, and most building materials, and by diffraction can bend around obstructions. Unlike other electromagnetic waves, they tend to be scattered rather than absorbed by objects larger than their wavelength. Using those properties, combined with their low energy, it's relatively easy to create and maintain radio signals, making them perfect for communication. Radio and TV signals, maritime navigation, cell phone towers, all of those work using mostly radio waves. Right beside these are microwaves, also used in communication, mainly satellite and radar. In astronomy, radio and microwave telescopes can detect faint and distant signals from the furthest corners of space. Like the cosmic wave background, an imprint of the recombination epoch, the moment when charged electrons and protons first became able to form electrically neutral hydrogen atoms. The CMB is known as the oldest light in the universe. Since before recombination, the universe was mostly plasma, too hot and dense for photons to move freely, essentially opaque. When it expanded just enough for the temperature to drop under 3000 K, electrons and nuclei first joined together, leaving photons to finally roam free. This is the moment the universe became transparent. However, this expansion doesn't stop. In all those billions years since then, it has enlarged so much that photons from the CMB got their wavelength stretched more and more until they fell into radio waves. So the only way to detect them, as well as many other astronomical phenomena, such as pulsar orbital periods, quasar emissions, and even merging galaxy clusters, is through radio and microwave astronomy. But information isn't the only thing light can carry. Microwaves are known for their heating properties, thanks to microwave ovens which use millimeter wavelengths to heat up water molecules in food. However, all wavelengths of light carry energy in the form of heat. Perhaps the EM range most famously associated with heat might be the infrared light, due to almost all blackbody radiation emitted by objects in a room temperature being in those wavelengths. That's why most thermal imaging cameras work within the infrared, because inside Earth's atmosphere, heat might as well be synonymous with infrared radiation. In astronomy, infrared is used to study our Sun. Most of its energy comes in this part of the spectrum. 527 watts in infrared radiation versus 445 watts in visible light. Infrared telescopes can also help with visible light observations by detecting previously visible wavelengths stretched into infrared by the universe's expansion. That will be one of the main missions of the James Webb Space Telescope, which hopes to launch this year and will operate in the near-infrared spectra. The easiest part of the EM spectrum for most of us to understand is the visible spectrum, going from 400 to about 800 terahertz. This is all of the universe we can actually see with our own eyes. This is what the cells in our retinas can pick up, and our brains interpret as light. Different colours have specific ranges inside the larger visible spectrum, and white light is the sum of all of them. This is the moon in the night sky, the blue oceans on the beach, the green leaves in the forest, your favourite colour, the face of the person you love, the movie you really like, everything you'll ever see in your entire life, less than 1/10 of a percent of the EM spectrum. Fortunately, humans are smart and have developed technology to see far beyond what our eyes can. And going beyond visible light only makes the universe stranger and more dangerous. After violet, the colour of visible light with the highest frequency, there's the aptly named ultraviolet light, mostly invisible to us outside black lights. Some UV photons have enough energy to break chemical bonds, causing ionization, a process in which electrons break away from atoms that is extremely harmful to living organisms because it damages DNA and can lead to cancer. In these wavelengths, our Sun turns from hero to villain, being the major source of all UV light that reaches our planet. If you get skin cancer, it's probably the Sun's fault. Lucky for us, only 10% of sunlight is in the ultraviolet range, and the Earth's atmosphere absorbs most of UV and higher frequencies, giving life essential protection against harmful radiation coming from our Sun and other cosmic sources. UV light also has a number of uses, from lasers to disinfection, and even photography. It's even responsible for the formation of vitamin D in most land vertebrates, including humans, thus being both beneficial and harmful to life. In astronomy, it's often used to penetrate some types of clouds and observe objects as close as auroras in Jupiter's atmosphere or star formations in other galaxies. After UV we find X-rays, known for being able to penetrate relatively thick objects without being much absorbed or scattered. Their wavelengths are usually just short enough to pass through molecules, and that's why they're greatly used in radiography, becoming almost synonymous with it. Due to Earth's atmosphere absorbing such short wavelengths, instruments to detect X-rays must be taken to high altitude by balloons, sounding rockets, and satellites. X-ray telescopes can see past most interstellar dust from nebulae and into high-energetic space phenomena like neutron stars, accretion disks, and even the Milky Way's extremely busy galactic centre. The champion for most energetic electromagnetic radiation, however, goes to gamma rays. Created by the radioactive decay of atomic nuclei, it's the shortest wavelength a photon can reach. They come from nuclear explosions on Earth and supernova or neutron star collisions in space. Gamma rays have wavelengths so small that not even a mirror can reflect them, the photons passing between the atoms without any problem. For that exact reason, protection against gamma rays is extremely difficult. Although our atmosphere would filter most of it, a direct hit from a source as far as 4,000 light years away could strip the Earth of almost all of its ozone layer, causing a mass extinction. In fact, A gamma-ray burst is one of the suggested explanations given by scientists for the Ordovician extinction that killed more than 85% of marine life about 450 million years ago. Fortunately, our galaxy has a diameter of more than 100,000 light-years, and about only one gamma-ray burst per millennia, so extinction by a giant black hole laser isn't something we should be worried about just now. We don't often correlate light with radio, satellite, or X-rays, but they are all part of the same thing. That just goes to show how something as trivial as light can take a whole larger meaning in astronomy. Photons really are the unsung heroes of the universe. Thanks for joining us this week in Access Astronomy. We hope to see you here next week as we continue to explore our strange and vast universe.